really what was going on. So to help us distinguish between all of these different options, well, this is where measures of dispersion or spread, I use dispersion because that's what the book uses. Spread makes more sense to me. This is where measures of spread are helpful in distinguishing all these different possibilities. So the first measure of dispersion is range. This is the easiest one to calculate. Range is calculated by taking the highest value in the set and subtracting the lowest value in the set. So max minus min is usually what we use. Highest minus lowest. It is reported as a single number, just one number. So if the highest test score was 100 and the lowest was 60, the range would be 40, and I got that from 100 minus 60 to give me 40. So that is your range. So it's a simple subtraction, max minus min gives you the range. That's not always enough to really tell us what's going on. So the best one we use, the most common one we use, is standard deviation. This is the most commonly reported measure of dispersion. And it is considered the deviation about the mean. That's how it translates. The deviation about the mean. Deviation is another word for difference. So it's how far each data point is from the mean. So if we're talking test scores, and I said the average test score was 70, and you got your exam back and you got an 85, your deviation from that mean would be a positive 15. I'm taking your 85 and subtracting the 70, and that gives me the deviation. So it's always the individual data value minus the mean, and that gives you your deviation. If you got a 65 on the test and the average was 70, your deviation would be negative 5. The negative means that you were below the mean. So sometimes deviations will be positive and sometimes they'll be negative. They'll be positive if your score was over the mean, negative if it's below. And if I take the time to subtract each data point from the average and add up all of those deviations, some of them will be positive, some of them will be negative. If I added up all those positive and negative numbers, the sum would be 0. Because that's what an average does. It takes all those differences, and if you add up all the positive and negative deviations, they all add up to 0. So there are some crazy looking formulas to calculate standard deviation. I do not expect you to be able to do this by hand. You're more than welcome to work it out by hand. I will explain how this formula works. However, your calculator can get this for you. So on page 132 of your textbook, it does go through step by step how to get standard deviation by hand. I always have students that try to work it out by hand. It is a lot of detailed, meticulous work, and generally something gets screwed up and your number is off. So I will show you how to use the calculator. I want to point out this new symbol. So the population standard deviation is symbolically represented by this weird symbol. This is kind of a loop with a lid. You kind of start at the top, go down and over, kind of like a cursive letter T where you don't pick up your pencil. So that's what it looks like, sigma. Other students make a little circle in a top, but I tend to make it like that. So that's lowercase Greek sigma. So that's lowercase sigma. And it is the population standard deviation. Population standard deviation. So we'll be seeing a lot of sigma, lowercase sigma, and mu. Mu, remember, is the population average. Sigma is the population standard deviation. So there's two different ways to calculate this. I personally think this formula makes more sense. This one's a little crazy. So I'm going to explain how this one was brought about, and you can look on your own if you want to see how they use this one. But this one makes more sense to me. So I'm, again, just going to walk you through how to calculate it by hand. I suggest using the calculator every time. So the next page just shows you the difference. So lowercase Greek letter sigma is used for population. That's that symbol. When we get to a sample, the lowercase English letter s is used for sample standard deviation. The calculator, it'll have s with a little subscript x. So it'll look like that, and that's the sample standard deviation. We'll get to that in just a minute. Alright, so here's my example. I'm just going to walk you through it. It's kind of confusing. Here are the same test scores from before. These are different test scores. Remember that the population average was 79. So the third column, they took each test score and subtracted 79. 82 minus 79, 77 minus 79. So it's always the score minus the mean. So they did that and got all of these deviations. Notice if we add them all up, we get 0. So what the formula does is it squares each deviation. So this deviation was 3. They squared it and got 9. This was -2, squared it and got 4, 11 squared. They squared all of these, and that takes off that negative. So squaring all of these, and then they take the sum of the squared deviations. So this is the sum of the squared deviations. If you already have a headache, that's okay. I, again, do not expect you to have to go through this process, but I want to show you how it's done. So it takes the sum of the squared deviations and divides by the size, which in this case was 10, and it gets you 96.4. Now, because we squared all of these, we have to go back and square root to kind of undo the squaring. So the standard deviation is the square root of that value. The square root of 96.4 works out to 9.8. So sigma would be about 9.8. So again, that process is tedious. It takes more time than it's worth, and the calculator can give us this value fairly easily. But that is how to work through that formula. This is explained on page 133 if you're interested. It also goes through how to use that other formula to do it. I'm not even going to worry about that. You end up with about the same answer. It is a different way to organize all of them, and I just find it unnecessary. So, we also have sample standard deviation. Again, it gives you this crazy formula. We don't really need to worry about it, but I do want to point out this little n-1. When we're talking about samples, we always do one less than the sample size. I'll explain it down here. So this n-1 is called the degrees of freedom. Don't really need to know what that means. Sometimes it's abbreviated DF. All you need to know is that DF, or degrees of freedom, is always n-1. The reason we subtract 1 is to give a little bit more buffer space when we're dealing with samples. Don't really worry about that part. Some students can understand that and some students can't. If we divide by a smaller number, it gives us a little bit bigger standard deviation, which for a sample gives us a little more cushion. Maybe that will make sense later, maybe it won't. Don't worry about it. I'll just know that the n-1 calculation is called the degrees of freedom. It's one less than the sample size. Alright, moving on. Don't worry too much about that. In the calculator, here's where we want to look. So, in Stat Edit, I'm going to put, where'd they go? I'm going to put those test scores again, back from table 10. So if you push up, clear, enter, L1 is empty. I'm going to put those test scores in again. Of them. Stat Calc 1var stats, and that's what we're looking at on that slide. Don't really worry about this one, just look over here. So here are the values that we got from the 1var stats. Remember the X bar was 79, and then there was a bunch of crazy stuff, and we scroll down to find the median. The first thing is the sum of the X values. Don't really need that. Then they take the sum of the X values squared. Don't really need that. So if it helps, you don't need either of those calculations. These are the two to look at. We have SX, that is a sample standard deviation. So if the problem talks about a sample, you would use S of X. If it says that it's the population, we use sigma X. S of X will always be a little bit bigger than sigma X, and don't really worry about why. Just know if you're dealing with a population, use the sigma X. If you're dealing with a sample, use S of X, and they will always be a little bit different. So if you see, that's about 9.8, which matched our by hand calculations. So SX and sigma X, hopefully you can see those in your calculator. SX, sigma X. And remember, if you scroll down, you can find the median, which we'll talk about more again at the end of chapter 3. All right. So the larger the standard deviation, the bigger this number is, the more spread out the data are. So larger standard deviation, more spread out. The smaller the standard deviation, the less spread out. Did not give myself enough room. The less spread out or closer the data are. So a large standard deviation tells you that your data are kind of pretty spaced out, a large range, whereas a small standard deviation means your data are pretty close together or a very small range. So standard deviation and range kind of measure just how far between all those data values we have. We'll see that a little bit better when we get into section, well, a little bit later in this section we'll see. That makes a little bit more sense. All right, so we've already done all of that. We put all those data into L1, we've done the 1 var stats, and we've calculated those values. All right, the next thing is variance. Variance, we don't worry too much in this course. All you need to know is that the variance is the square of the standard deviation. So population variance is the standard deviation of the population, and all you have to do is square it. That'll give you variance. Sample variance is the sample standard deviation squared, and that gives you your answer. I think there's one homework question about variance. Not important as much in this course as it would be in a more advanced statistics course. So if you need more explanation of that, it's on page 136. Okay, so the empirical rule is the next topic in section 3.2. Again, these are bigger sections that has a lot of important information. The empirical rule is something that we will use a lot in this course, especially when we get down to chapter 7. Page 137 is where it's explained. So if the data are bell-shaped, and that's based on the histogram, if they're bell-shaped, we can use the mean and the standard deviation to create a symmetrical bell curve. So for an example, let's say that the average test score is 70 with a standard deviation of 10. So I put my test scores in, I figured out that mu is 70 and sigma is 10. That's just an example. If we draw a symmetrical bell curve that kind of curves up, over the top, and back down, which we'll be drawing a lot of, the very center line, right down the middle, is where mu is always at. If it's a symmetrical distribution, the mean is always in the middle. So underneath, I'm going to put 70, just for this example. Let's say the mean is at 70. And then a little bit out to the right, and a little bit out to the left of that, we always draw 2 vertical lines, one on either side. This is 1 standard deviation above the mean, and this is -1 or 1 standard deviation below the mean. So my sigma is 10. So if my test average is 70, and if I go 1 standard deviation above that, that would put me at 80. So I'm adding 10. If I subtract 10, that puts me down at 60. Then we draw another line, a little lower on the curve, and I add 10 more. This is 2 standard deviations, and that will take me to 90. And if I subtract 10 more, that'll be -2 standard deviations, and that will put me down at 50. We always go one more, and it's always at the very end of the curve, so we always go 3. 3 standard deviations, we'd add another 10, and that would get us to 100, or subtract another 10, that would get us down to 40. So every single bell curve that we're going to draw, we're going to take the mean and put it in the middle. We're going to add 1 standard deviation, 2, and then 3, and subtract 1, subtract 2, and subtract 3. This is a normal way, standard way to draw this bell curve. Mean in the middle, 3 standard deviations to the right, and 3 to the left. So these numbers are always true. The ones down here are just for this particular example. We're going to use this to help us understand how bell curves work using what's called the empirical rule. All right, so your next slide has a bunch of empty boxes. And this can be a little confusing. So if you need to take a break, maybe pause, take a break, and then come back refreshed for this part of the video. This is very, very important. This is the empirical rule. All right. So we have a lot going on here. I want to focus first on these top 3 boxes. The empirical rule is on your formula chart. If you look at this is organized in 2 columns for chapter 3. If you look at the bottom of the first column, you'll see empirical rule. And it says if the shape of the distribution is bell-shaped, then approximately 68% of the data lie within 1 standard deviation of the mean. So that first number is 68%. We're going to put that down here. 68% of your data fall, remember the mean's in the middle, either 1 standard deviation below or 1 standard deviation above the mean. If you look on the empirical rule in that chart again, it says approximately 95% of the data lie within 2 standard deviations of the mean. So the box above that, 95% lie either 2 up or 2 down. So within 2 standard deviations. And finally, if you look on the chart, it says 99.7% of the data lie within 3 standard deviations of the mean. 99.7, 3 up or 3 down. So almost the entire curve, the entire set of data is represented within 3 standard deviations, 99.7%. There's a little tiny, tiny extreme above that and a teeny, tiny extreme below that. Very small amount. So given those 3 numbers, we can actually break this curve down into several little tiny pieces. I'm going to show you how to do that step by step. Once it's all done, some students choose to memorize all these little tiny numbers. I don't recommend that because students get them mixed up very easily. If you can remember these 3 numbers that are on your chart, and you can remember how to draw those, you can easily get all those little tiny numbers. So just bear with me. We're going to work through this. Hopefully it will make sense how I'm breaking this down. All right. So I want you to focus all of your attention within 1 standard deviation. So just ignore those, just focus your attention right there on 68%. We know this bell curve is symmetrical, so right down the middle is the mean. So if I take 68% and split it in half, you can decide how much of the curve is covered in just this little section and then just this little section. So 68 cut it in half, that gives us 34%. So 34% of the data are in this little section, and 34% of the data are in that little section. And this will come in handy a little bit later. Now if we expand open to 95%, we're looking at that middle 68 and a little bit down here and a little bit up here. So I'm going to subtract 95 minus 68. Hopefully you can see that. That gives me 27%. So the difference between this inside piece and these outside pieces is 27%. There's half of it down here and half of it up here, that leftover. So I'm going to divide that in half, and it gives me 13.5. That means that 13.5% of my data are just in this little section between 2 and 1 standard deviations below the mean, and 13.5% are just in that little section between 1 and 2 standard deviations above the mean. Hopefully you're with me so far. Now we're going to look at the difference between 95 and 99.7. So we're looking here and here at these little differences. So if I do 99.7 and the difference from 95, I get 4.7. That's the little bit between 2 and 3 standard deviations. If I take that and split it in half, I get 2.35. So that means that 2.35% of the data are between 2 and 3 standard deviations below the mean, and 2.35% of the data are between 2 and 3 standard deviations above the mean. Hopefully you're with me so far. Now there's a little teeny tiny bit outside of 3 standard deviations, and so if we take 100, which would be 100% of the data, and subtract 99.7, that gives me a little tiny bit of 0.3. If I divide that in half, it gives me 0.15. That's a very small amount. 0.15% of data are after or below 3 standard deviations below the mean, and 0.15% of the data are above 3 standard deviations above the mean. If I take all these little tiny broken down numbers and add them all up, I should get 100%. So using these 3 values and your knowledge of symmetry, and knowing that the entire curve represents 100%, you can break down each little tiny section into a percentage. Again, some students choose to memorize these. They'll memorize the bottom half and then reflect it over. A lot of students get these little ones kind of mixed up, so just be careful if you're going to choose to memorize. I recommend not worrying about all those numbers, remembering these 3 that are on the chart, and then using that knowledge to fill in the rest. So that's just my recommendation. All right. So this empirical rule is going to be very powerful. It's going to help us answer a lot of questions. So I'm going to kind of leave it out so we can refer to it. So here's an example from that same test statistics about the average. Let me show you. We're going to use that same example of the average being 70 with a standard deviation of 10. So using this example and our knowledge of the bell curve, we're going to answer these 3 questions. It says approximately what % of students made an 80 or better on the exam, an 80 or better. So I'm going to kind of look at both curves here. 80 or better. So 80 was 1 standard deviation above the mean. So this is where 80 was. I'm just going to write these on here to help you. 90, 100, 60, 50, 40. There we go. So I'm just using that example where the mean was 70 and the standard deviation was 10. Okay, so using that example, approximately what % of students made an 80 or better on the exam? So here's 80 or better, so anything above 80. So if I take 13.5 and I add 2.35 and I add 0.15, whoops, that should give me 16%. So 16% of the class made an 80 or better on the exam. The next question, approximately what % of students made below a 60 on the exam? So here's 60 and below. Again, I'm going to add those 3 numbers. 0.15 plus 2.35 plus 13.5. That should give me the same answer, 16. So 16% of students made below a 60. Everything's symmetrical, so that kind of helps you understand. And then approximately what % of students made between a 60 and a 90 on the exam? So 60 is here, 90 is here, between would be this 34%, this 34%, and this 13.5%. Add all those up, gives us 81.5%. And we can only use this rule if the data are approximately bell-shaped, which it will tell you in the problem if they are bell-shaped. I'm going to pause there and record the rest in just a minute.